for a region in the three-dimensional space, we have many choice of substitutions. Okay, for the triple integral, the region could be very complicated, but there's some regions. Idea is we're trying to find the pre-image of that region. The pre-image has a better shape, so we can easily set up iterative integrals for that region. Okay, so the idea is that here's a region in the three-dimensional space, right? Okay, and then we trying to find out much better region, maybe a portion, it's rectangular shape. Okay, could be like that. Okay, it could be like that. Okay, so this could be let's use other variables. This could be u, v, w. Okay, and I try to give you the general idea. Okay, so you have x is going to be x depends on u, v, w, and the y is going to be u, v, w. Here z equals also u, v, w. Okay, so if you have a function here x, y, z, and that is a region, that's called R, okay? And here's R prime, okay? So on the left-hand side, on the right-hand side, you have a triple integral, okay? And we try to find, this is in one-dimension case, we call substitution, okay? This is just transform from one region to another region. So we try to find the triple integral, okay, which should be equal to the one on the right-hand side. So clearly, this still x, y, z, okay? X is replaced by u, v, w. Y will be replaced by u, v, w, okay? Now, there will be addition term. So this is my notation. This is a kind of like a derivative, and this is a v prime, okay? So v prime is du, dv, dw, and here dv is dx, dy, dz. Okay, so this is a formula, very general formula. Okay. Now, what happens if we have the polar coordinates? Okay, this is what we call the polar transformation in the substitution. It's okay. So if the first case, right? If x equals r cosine theta, y equals r sine theta, z equals z, then you have a variable from r theta z to x, y, z, right? That's a substitution. All right. So what we got here is we find out this is a u, v, w. Okay. So x, y, z, r theta z. This is just equal to r. Okay, I already did the computation for you. So we have the formula. If here's x, y, z, dv, and that will be r prime. Okay, f x, y, z. You can replace x by r cosine theta, r sine theta, z. Okay, there will be addition term r here because this part, then dv prime. Okay. Now, what I'm going to do today is talk about another substitution. So this substitution is given by the following formula: I equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. Now, what is theta and phi here? Okay. What is the theta and phi here? Okay. So in the space, okay, this is a region, right? An arbitrary point x, y, z can be described using the following formula. Okay, x. So this angle is going to be phi. Okay, and so first of all, you project the point onto x, y, z plane, x, y plane. Okay, so the component 0. So this will be R, right? It's dense. This will be rho. Okay. So the relationship R is going to be, okay, rho sine phi. Okay, why? Because this is a right triangle, right? This is a right triangle. So sine phi gives the length of this side. Okay, this is R. Okay, and so once you have an R, then you have an angle here, theta. So then x equals R cosine theta, y equals R sine theta. Okay, so you have this two, really, right? So R is a rho sine phi. Okay, now what is z? Z is going to be height of that point. So z is going to be rho cosine phi. Okay, so that gives you the above formula when you replace R by R sine phi. Okay, this is called the spherical coordinate. Okay, this is called the spherical coordinate. Okay, so now we compute. Let's compute this one. R rho theta phi. Okay, let's compute this. Okay, what does that mean? This is a determinant of the matrix. Partial derivative of x with respect to rho, partial derivative of y with respect to rho, partial derivative of z with respect to rho. Then okay, then you have the last one. Okay, so let's compute it. The first one, when you differentiate, with respect to rho, this is just sine phi cosine theta. Okay, here's a sine phi sine theta. The last one is cosine phi. Okay, that's the first derivative. Then when you differentiate with the theta, you get rho cosine. This is still sine phi, but that would be sine theta negative. Okay, and this would be rho sine phi cosine theta. The last one will be 0. Okay, because that's the derivative with respect to theta. Then we differentiate with respect to phi. That be rho cosine phi cosine theta, rho cosine phi sine theta. Then the last one will be negative rho and sine phi. Okay, now you have to find as a determinant. Okay, you have to find a determinant. And this 3x3 matrix, do you still remember how to find the determinant? Right, you find the determinant, you can do the following. You expand along any of the lines, along this line maybe, right? So it will be sine phi cosine theta. And then the matrix of this, determinant of this, rho sine phi cosine theta. Okay, and then negative sine phi sine theta, and you get the matrix of this two. Okay, negative rho sine phi sine theta 0, and rho cosine phi cosine theta, the negative rho sine phi. Okay, and the last one will be this matrix here. okay? Negative rho sine phi sine theta, rho sine phi cosine theta. Right? Then lots of terms, right? Here, the first term will be, I think it'll be negative rho square. And yeah, only this line, okay? So you will get sine phi square, then sine phi cube theta. Then you have a cosine square theta, okay? Okay, the second one, will be, that's negative, it's a rho square, sine phi, and you have sine cube, and the sine theta, and the sine square theta, okay? And the last one, it's a negative. So you have a negative rho square. So let's see, sine phi, cosine phi. Okay, then you have a sine square. You have a sine phi, yeah, you have a cosine square phi. Okay, then you have a sine square theta. But okay, I'll have to erase this. This is a little bit complicated. Then you have to finish the matrix first. Then you multiply by the term outside. So let's see. The cross product, right? And the cosine phi, sine phi, and the sine theta, and here a cosine theta. Okay, so you have a rho square, okay, and sine phi and cosine square phi. That's it. There's no theta here involved. Theta is already gone because sine square theta plus cosine square theta equals 1. All right. Then you have to group them together. The first two gives you, this 2 gives you 1, okay, because cosine square theta plus sine square theta 1. Okay. Then you take sine this out. So finally, you will get this term. Okay, now it's negative, right? It's a determinant. So this is actually, we have to go back to the formula here. This should be the absolute value of, mine depends on which order you define the derivative, okay? So this is going to be, this notation, this actually is the absolute value of the determinant. So I should, I should put another bar here. This is absolute value, okay? This is absolute value, okay? So this is a determinant of the matrix, positive, okay? Anyway, so after we simplify and take an absolute value, this will be R prime, F, and X, Y, Z can represent, and then you have a rho square, sine theta, and this is the triple integral. Okay. Now I hope our region R prime is better. So it's usually a rectangular type. So then you can easily set up the triple integral. Okay. So this is our formula. Okay. Now you can also discover some new transformation, new substitution, and you have to derive the formula by yourself. Okay. Okay. So before we do this, let's get familiar with this transformation. Okay, suppose you have a point. Here's the example. You have a point has coordinates square root 3, -1, 2, square root 3. Okay, and I want to find out the phi, and I also want it's projected to here. I want to find the theta, and I want to find the rho. Okay. How can I do that? Well, This will be x, right? Based on the above formula, rho square is going to be x squared plus y squared plus z squared. Okay, so you can determine that one first. Okay, you can determine that one first. That will be square 3 square plus -1 square plus 2 square 3 square. Okay, yeah, go back to here. You see our transformation here. You see, when you square all of them, you get rho square. Okay. Yeah, so rho square is going to be x squared plus y squared plus z squared. The distance between the point and the origin. So it's going to be 3 plus 1. And that will be 12, right? 12. So that's going to be 16. Rho is going to be 4. Okay, good. Then how do you find the theta? So this is going to be the point projection of the point onto the xy plane. All right, so for this point on the xy plane, you know how to find the I and the theta, right? I is going to be just x squared plus y squared. Okay, this is actually is going to be I is going to be r squared is going to be x squared plus y squared. Okay, x squared. So square 3 square plus -1 square equals 4. Okay, so I is 2. Okay, but on the other hand, how to get R? I is this is R, right? So I is going to be rho sine phi, right? No sine phi. This is right angle. That's the right angle. That's the right triangle. So we have 2 equals 4 sine phi. That implies sine phi equals 1/2. That implies phi is going to be pi over 6. Okay. So yeah. So now I'm going to get theta. Okay. So we know that x equals r cosine theta, y equals r sine theta on the xy plane. So my x is going to be square root 3. Y is -1, right? But we already know I is 2. So can I get theta? The answer is yes. Cosine theta equals square root 3 over 2. Sine theta equals -1/2. Remember, theta is between 0 and 2 pi, okay? Phi is between 0 and pi. Okay. So from the picture, you can see that the maximum value for the phi is from north pole to the south pole. Phi increase from 0 to pi. Okay. But then you have to rotate around the z-axis, then get complete circle, then get so theta. But these two equations uniquely determine the theta. Now, in which quadrant cosine theta is positive, sine theta will be negative here. Okay, so this is the angle theta. Okay, this is angle theta. It's in third quadrant. But how do you solve this equation? You can look at the references angle. Okay, cosine of a references angle equals this, and sine references angle is equal to positive. Okay, the references angle is always the angle between 0 and pi over 2. So there's a unique angle here. Right, that's a references angle. So theta equals 2 pi minus the references angle. So it's 11 pi over 6. Okay, 11 pi over 6. So that is theta. Now you have, you have r rho phi theta or phi. Which one is first? Okay, yeah, we have to see the order, right? So let me check. Okay, which one's first? We usually use rho theta phi. Okay, theta first. Okay, rho theta phi. Then there will be 4. Theta is 11 pi over 6. and the phi is pi over 6, and that corresponds to xyz. xyz is a square of 3, -1, 2 square of 3. Okay. Yeah. So this is yeah. So square of 3, -1, 2 square of 3 is the image of this transformation of the point 4 pi, 11 pi over 6, pi over 6. Okay, this is how do we, yeah, we understand the rho, theta, and the phi. Okay. All right, now we are going to look at the following example. That's a problem 22 from the book. Okay, we evaluate the triple integral. This is y square z square dv. Okay, here's a description. Are lines above the cone determined by pi over 3, okay, and the phi is pi over 3, and below the sphere. All right, what does that mean? That means we already using the spherical coordinates to describe the region. Okay, here's the region. Okay, I can describe it in a different way. This is a cone, right? The sphere was radius 1. So so I can say that using x, y, z, you know. Yeah, this is a cone. Okay, all the points with a fixed phi equals pi over 3, you get a cone. Okay, we can describe this cone using the equation in x, y, z. Okay, and below the sphere. Okay, below the sphere, above the cone. Okay, so that is the region I'm talking about. Okay, that's the region I'm talking about. All right, that's the E. That's the region R. Okay. So you can rho equals 1. You can describe it as x squared plus y squared plus z squared equals 1. Okay. Now, how can I describe phi? Phi. This is a cone, right? Yeah. Okay. So the cone, phi is fixed. Okay. So that means for phi equals pi over 3, that implies x equals rho is 1, right? Sine phi. Sine phi is a square of 3 over 2 cosine theta. Y equals sine phi and sine theta. Z is going to be square of 3. Hold on. Z is going to be square of 3. Yeah. So this is a rho. Okay. The rho is not fixed. Okay. This is a rho. Okay. And that is not different. Okay. So this is in general. Okay. General formula. And that will be cosine phi. So it's 1/2. Okay. Yeah. Only phi is fixed. So x, y, z are described by this, but you can also modify this, okay, in a different way, you know. So you can square it, right? So you can say x squared plus y squared. So you will get 3 over 4 rho squared, right? Because cosine squared plus sine squared is going to be 1. And on the other hand, z squared equals a quarter of rho squared. So I can replace rho squared by 4z squared. So I get x squared plus y squared equals 3z squared. Okay. So this equation, the cone, can also be described by this equation. Okay. This is a cone. Okay. Now we can assume that z is going to be greater than 0, okay? Because it's otherwise it describes the two parts here. One is above the xy plane, other one is below the xy plane. Okay, so then there are different ways to describe the cone. So you're above the cone, equation, the Cartesian equation for the cone is x squared plus y squared equals 3z squared. Okay, all right, but we probably don't need that. Okay, so we're going to find under this transformation. Okay, under this transformation, we're going to, yeah, this is rho sine phi cosine theta y equals rho sine phi sine theta and z equals rho cosine phi. I want to find the pre-image of the domain. Here's a rho, here's theta, here's this phi. Okay, so how do we describe the point? I think the largest possible angle is pi over 3. So clearly, phi is between 0 and pi over 3, right? The rho, the value for the rho is between 0 and 1. Okay, how about theta? No restriction on the theta. So theta is, you rotate around the whole circle. So theta is between pi over 2. So actually you get a box. Okay, 2 pi. Here's a 1. And this will be pi over 3. All right, this region, this is a R prime. So this box is mapped to the above cone, right? It's surprised, yeah. But actually, some as a boundary will be collapsed to a point someplace or collapsed to the line. So that's why you end up with a cone, okay? All right, so this is our region. Okay, now we are going to go back to the integral. So this is a triple integral R, and here's y squared, z squared, and dv, right? This is supposed to be R prime. At this moment, I still put the y squared there. I'm not going to replace y. Y is actually low sine phi sine theta. Okay. Now, what I want to put here is an additional part from the determinant, right? We got the formula already from the determinant. It says that it's going to be rho square sine phi. Okay. So that will be rho square sine phi. Okay. Then d prime. Okay. This d prime is dr, d rho, d theta, d phi. Okay. So this is a triple integral. So it doesn't matter which one is first because this is a square. So rho is from 0 to 1, phi is from 0 to 2 pi, theta, yeah, phi is from 0 to pi over 3, okay? So y is going to be, y squared is going to be rho sine phi sine theta squared, okay? And here rho cosine phi squared, right? Z squared, right? Yeah. And then you have a rho square sine phi. Then here inside d phi, then d theta, then d rho. Okay. So this is my dv prime, right? So you can express this. So so now you get the integral of well, okay. So you can those three variables are quite yeah, you can separate them. Have a rho square, rho square, rho square, rho to the power 6. And then you have a sine square, sine cube phi, cosine square phi. Okay. Then you have a sine square theta, right? Sine square phi, cosine square phi, and sine phi. So you have sine cube phi. So d phi, d theta, d rho. Okay. And then you have to evaluate the integral Actually, you can do one by one and separate. Okay. So this is a product of three variables. Okay. So actually, you can get like from 0 to row to 60 row. It's separate. You know why? Yeah. So here's sine square theta and d theta. Okay. In general, it cannot be done like that. Okay. Pi over 3, the sine cube phi, cosine square phi d phi. Okay. So you evaluate each of the integrals. Yeah, the reason is you can do that is, first of all, you evaluate this, right? And the row to the 6 sine theta can be taken out because they're independent. So finally, you will get product of those integrals. And the first one will be just 1/7. Okay, it's easy to see. The second one, because the antiderivative will be 1 minus cosine 2 theta divided by 2, right? Yes. So the integral of the cosine 2 theta will be 0. The first one will be 1/2. It's actually just pi. Okay. Now the difficult part is the last one. The last one we have to let's do this. Yeah, I'm going to put the answer here. The last one is trying to find the antiderivative of this function. Okay. And how to do that? Well, you will get sine cube phi is going to be sine square phi, cosine square phi, and the sine phi and d phi. Then you use a substitution. The substitution will be let u to be cosine phi. Okay. Then du is going to be negative sine phi d phi. Okay. So sine square phi is going to be 1 minus cosine square phi, right? Okay. So you will get 1 minus u square and then negative du. Okay. Because du equals negative sine phi d phi. Okay. All right. So you will get 1 minus u. Okay. Actually, u to the 4th power minus u squared du. So the antiderivative is this. Okay. So you replace it by 1/5 and the cosine to the power of x minus. Okay. So this is the antiderivative. All right. And then the integral from 0 to pi over 3. Okay. Is going to be it's going to be the difference of the values at two endpoints. So the first one is cosine pi over 3 to the 5th minus 1/3 cosine pi over 3 cubed. Okay, that's the first part. The second part will be cosine 0. Okay. And cosine pi over 3 is 1/2. Okay, I'm not able to simplify right now. It takes too much time. So this is the answer. Okay, this is the answer. And then you put it here. You get this part. Okay. So this is I cannot even copy to there. It's a very complicated term. Okay. Yeah. So you can put it back. Okay. So this will be the answer. So the domain, the region is pretty good. It's a box, right? So you can easily determine the yeah, you can easily evaluate the triple integral. Okay. Now, now let's take a look at similar problems, number 30. Okay. So this time you are given the equation for the cone in Cartesian coordinate. Okay. So find the find the volume of the solid that lies within the sphere x squared plus y squared plus z squared equals 4 above the xy plane, right? And below the cone. Now, the cone this time, it is given by the formula z equals square root x squared plus y squared. So this is a cone above the xy plane because z never be negative. So how can I describe this? Okay, so this is a sphere. Okay, the radius is going to be 2. So, so how do you describe the cone? The cone looks like that. Okay, this is a cone. Okay, so there's the intersection here. Okay, so it's below the cone, above the xy plane. So the region we're trying to find out is this part. Okay, so that is a yeah, that is a solid. Okay. So so the volume, write down the formula first. So the volume is going to be the triple integral of that region, right, of the constant function 1. So that's the volume. So all you needed to do is to, describe that region using spherical coordinates. So an arbitrary point x, y, z, right? So that's transformation. Let me write down this transformation again. So this will be sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Now, what is a phi? Phi is this angle phi, right? So there was no, so clearly phi, so phi is between, phi actually is less than pi over 2, but greater than some angle. And that angle, yeah, we have to figure it out, okay? The angle is determined by the cone. I think that angle must be pi over 4, okay? The reason is, look at this, right? Look at this z, just look at the, this is y axis and z axis, right? And the cone equation of a cone is becomes z equals y when x equals 0, right? Because when x equals 0, z equals square of x. So this is a strict line. That's why it's a pi over 4. Pi over 4, okay? So you get pi over 4. And the rho is clearly it's between 0 and 2. Theta is between 0 and 2 pi, no restriction on theta. Yeah, you can rotate around the z-axis completely. Okay, so that's it. So this is my R prime. So now the volume is going to become another integral over the R prime. And 1 is 1, right? So it's rho square sine phi d phi prime. Okay. It's constant 1 times this. Okay. So now you can, it's a box, right? R prime is box. So it's easy to write down this integrals and doesn't matter which one is first for the box. Okay, so you can say rho is from 0 to 2, and the theta is from 0 to 2 pi, phi is from pi over 4 to pi over 2. Okay. So the entire derivative of sine phi is going to be negative cosine phi, right? And then evaluate the two endpoints. Okay. And that is going to be, okay, cosine phi is going to be 0. So this positive square 2 over 2. Cosine pi over 2 is 0. And the cosine pi over 4 is 2 square root 2. Okay. Right. So now this is independent of theta, right? This is independent of theta. So you can just multiply by 2 pi. Okay, this is a square 2. Okay, rho square 2 times 2 pi d rho. Okay, so cancel it out. You take this out, and the entire derivative of rho square is going to be 1/3 rho cube. Okay, so the answer will be, okay, will be this. Okay, so let's simplify it. It's going to be 8 square 2 pi over 3. All right, so that is the volume. Pretty strange number, right? So those two regions are still pretty nice. And now, if you don't want to use the polar coordinates, you probably end up with very complicated iterative integrals. Okay. Yeah, let's try to go back to the problem. If I don't want to, yeah, let's see. Okay, I'm going to go back to the problem. Okay, so here's another way to do, right? This is a cone. Okay, I'm going to all right. Okay. So if you do not use strict coordinates, can we set up an iterative integral? So the answer is yes. Okay. What I'm going to do is there are two types of iterative integral you can set up, but I prefer the second one. So this is the triple integral, right? This is a dv, right? So what I'm going to do is I'm going to cut this solid into slice. Okay. Okay. Right. So that, remember, we that's a, actually this is from Math 165 problem. Okay. So you take you fix the z. Yeah. So in order to set up this, right? So you have to say for each z, okay, z is between 0 and the 1 on the top. Now, this equation is this line actually is z equals y, right? When x equals 0, right? So so when the radius, this rho is going to be 2, right? So this is going to be, I think, a square of 2. Okay, so z is between 0 and square 2. Okay, that's a square of 2 on the top. So for each z, you get the cross section. okay, for each fixed z. And so x, y are in this disk, right? Was removed, the small disk is removed. So this is I'm talking about, right? So that disk I call it dz. So x, y is in dz. Now, what is the equation for x, y? If you project the x squared plus y squared is smaller than equal to 4 minus z squared, because it's inside the sphere, okay? But it's greater than z squared. Yeah, because the equation for the equation for the cone is z squared equals x squared plus y squared. Okay. Yeah, look at this point. Look at this point on the disk, right? Z is fixed. When z changes, you get family of disks from top to the bottom. Okay. So this is inside the sphere. That's why x squared plus y squared should be less than or equal to 4 minus z squared. Because when equal to 4 minus z squared, then this is the point on the sphere. But also should be outside the cone, okay? Outside the cone. That's why should be greater than z squared, okay? Because the cone equation for the cone is z squared equals x squared plus y squared, okay? Okay, actually, for the fixed z is the radius of the smaller circle inside, okay? So that's why you have this identity, okay? But that's good, right? So now you have triple iterative integral. First of all, z is from 0 to square root 2. Then you evaluate this, right? Clear. Okay. Now you get, this is just the area of that disk. Okay. And what is the area of that disk? Well, it's the difference of the two radius. One is a 4 minus z squared and square. Another one is just a z squared, then square, right? So you get a polynomial. Okay, you get polynomial. When you square it, it's a 16 minus 8z squared plus z to the fourth power and minus z to the fourth power, right? So this cancels out. Not surprised. The antiderivative is 16z minus 8 over 3z cubed, and evaluate the two endpoints. So you will get 16 square root 2, 8 over 3, square root 2 cubed. Okay. So we have to simplify a little bit. This is a square root 2, that'll be 2, square root 2. So I take a square root 2 out. I take a square root 2 out, right? So I get, what do I get here? Okay, 8 times 16 is also, it should take it out, right? So it's square root 2 taken out. It's a 2 over 3. Yeah, 1 minus 1 third. So my answer is a 32. Did I get the same answer or not? Did I get the same answer? Wait a minute. We got 8 square root 2 over 3. Okay. Right. So I made a mistake somewhere. So let me check. Okay. Oh, I see. I made a mistake somewhere here. This is it's a 2. The radius. It's xy. Let me check. What is my radius? Because the radius. Let's go back. Okay. I'm confused. The radius is going to be, yeah, it's 4, right? Yeah, it's 4. Okay, it's not 4 squared, just 4. So that was my mistake. Yeah, so it's 4. Yeah, 4 minus z square. That's okay, right? Okay, I have to double check this. I found out a bigger number here. Oh, okay, I got it. Okay, so that's what I must say. So when you have the upper bound, right? So this is upper bound, okay? But that's not the radius is going to be square root of 4 minus r squared. So it's a square 4 minus. That's a mistake, yeah. Okay. And here's radius is r, so there's no square here. Radius is z, okay? So z, okay? That's why I made a computation mistakes, okay? So let me erase this part. It's easy to make mistakes. Okay, so the radius, you see, when you say equation, yeah, equation, all right, so this is a pi, and then it's minus z square, okay, and then minus z square. So z square is not canceled out. Okay, 4 minus 2z square, then the antiderivative is going to be pi 4z minus 2 over 3z cubed. Okay, so finally you will get the same answer. Okay, so you will get pi 4 square root 2 minus, this will be 2 square root 2. Okay, yes, yes. So now it's going to be 8 square root 2 pi over 3. The same answer. So for this particular problem, you can use you don't need to use spherical coordinates to solve the problem. Okay, so some problems we do not specify which method you have to use. Okay, then you can set up integrals, iterative integrals directly. Okay. Yeah, let's set up another integral. Let's look at the problem from the book. Another problem. Okay. Okay. Right, that's I'm just going to set up integrals. Okay, so it's 24. Okay, evaluate this triple integral. Okay, and here R is a solid hemisphere. Okay, x squared plus y squared plus z squared equals 4 equals 9. Okay, less than equal to 9. And y is greater than equal to 0. Now, what does that mean? That means the radius is going to be 3, right? Right. So this is about the upper hemisphere. No, y is greater than 0, and not z greater than 0, right? So this is about this portion. I cannot draw clearly. Yeah, this is a part. Okay. Positive y. Okay. So how can I set up iterative integrals for this problem? There are there are many ways to do, honestly. Okay. If you want to use without using the sphere coordinates, and then you fix the y, you get cross section, and that is called a dy, right? I want to know what is dy, right? Okay. For that disk, yeah, for each y between 0 and 3. Okay, the x, y are determined by this equation. Xz. Okay, so xz. Okay, x squared plus z squared is less than or equal to 9 minus y squared. Okay, so that means dy, the domain determined by y, is given by this equation. Okay, so the radius is in this case the radius is going to be 9 minus y squared of 1 minus y. Okay, all right. So the triple integral is going to be the single integral. Right, first it's y is from 0 to 9. Okay, and then a double integral, that will be dA, okay, and dy. Now the good part is y is independent of dy. Okay, so this is just the integral with respect to dx dz, right? So y is a constant. We fixed here, so you can take y out. Okay, and that just is the area of that disk. That is the area of the disk. So it's from 0 to 9 y squared. That is the area of the disk. Area of the disk is pi times the square of the radius. Square of the radius is 9 minus y squared, because I is going to be 9 minus y squared. And it turns out to be not complicated, right? So you will get 9y squared minus y to the 4th power. So you find the antiderivative. It's 9 over 3y cubed, 1 of. Right? So let's simplify it. So you get here 3, 9 cubed, 9 to the 5th. Okay. We can take 9 cubed out. Okay. So you will get 3 minus 9 squared over 5. Okay. This is going to be, wait a minute. Why this is going to be negative? Okay, let me double check. This shouldn't be a negative number. Okay. Oh, you see, I have another mistakes here. I copied wrong. It's a 3. No wonder, right? See, when you get a negative number, it's clearly it's wrong. So you have to go back to double check it. Okay, it's easy to make a mistake. So when I say y is between 0 and 3, I put a 9 here. Okay, I put a 9 here. Okay, so now you can. Now this must be positive. Okay, it's pi and 3 cubed minus here 3 to the 5th. Okay, so you can take 3 to the 4th power out, and you will get pi 2 times this. Okay, this is answer. Okay. All right. So now I already got the answer, right? So how about spherical coordinates? Okay. How about spherical coordinates? We look at this picture again, right? So this is a picture here. Y is greater than or equal to 0. So an arbitrary point here, this is a phi, that's a theta. So spherical coordinates, x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. Okay. So clearly, because we are talking about this semi-hemisphere from here to here, right? So clearly, rho is between 0 and 3, right? That's the radius. And the phi is between 0 and pi. But theta, only from 0 to pi, because it's not a complete circle. Okay, theta, right? It's from here all the way to the back side. So this is my R prime. Okay, this is my R, right? Okay, so remember our triple integral, right? This is the y squared dv, right? That's what I remember, right? So this should be equal to R prime. Y is going to be rho sine phi sine theta squared, okay? And then you have a rho square and the sine phi, okay, dv prime. Now, it turns out to be more complicated than we thought, right? The functions. And then let's simplify a little bit. You have a rho to the fourth power, okay? You have a sine cube phi, right? And you have a sine square theta, dv prime. So you have to evaluate sine cube phi and the sine square theta, okay? So, but because this is a rectangular box, so it's from 0 to 3, from 0 to pi, from 0 to pi. And this is the inside one is a phi, theta, and rho. Okay. So we have to evaluate the integral one by one, each of them. It's about phi, right? So what is the integral from 0 to pi? And that's the phi. Okay. How do you do that? Oh, well, we have to do this way. It's going to be sine square phi sine phi d phi. And then you have to use a substitution again, right? Okay. Use a substitution, you let u to be cosine phi. Then when phi equals 0, you get to 1. And then you get a negative 1 phi equals pi. It's 1 minus u squared. And the du equals negative cosine phi d phi. So that will be negative du. Okay. So I will get, okay. No, actually it's still 1 minus u squared. Okay. Because I changed get rid of a negative sign. So it's 1 minus u squared. So antiderivative from negative to positive 1. And it will be 4 over 3. Okay, I just write down that. Okay, it will be 4 over 3. Okay, so you finish that part. Then you have to remember, you have to complete this part. Okay, this part, you have to write 1 minus cosine 2 theta, this is, okay? Now the integral cosine 2 theta from 0 to pi is going to be 0, okay? Because when theta changes from 0 to 2 pi, no, from 0 to pi, cosine 2 theta change from 0 to 2 pi. So negative positive all cancel out. So what do we get is going to only get pi over 2. Okay. All right, we are almost done. Yeah, all we have to do is just go back to this integral. And yeah, so we go back to that integral. I think this triple integral and the antiderivative of rho to the fourth power is going to be, yeah, let me write down here. 5 to the 3 to the 5th times the second is pi over 3 and pi over 2. Okay, so you will get 3 to the 4th power and pi over 5. Is this what we got? Maybe. Yeah. So we will go back to this. Yeah, that's what we got, right? All right, and this example show you, okay, yes, you can use a strict coordinates, but it takes more time actually, okay, to solve the problem than the use a tradition method. You know, you use a tradition method, but that requires some you know, this is requires some knowledge about 3D geometry. Okay, so you can for the triple integral, right? Let me mention two iterative integrals again. So if you have a region in the space, right? This is right. How to change it to the iterative integral. Okay, you can do two different ways. One is, I just give example. One is if you can project it to the z-axis, it's A and the B, right? Then for each z, you get cross section. Okay, that cross section we call the dz. Okay, so the integral from A to B, and then you have a double integral inside. Okay, so you evaluate the double integral on dz first. Dz is determined by, dz actually is on the xy plane. Okay, dz is actually determined by the xy. Okay, yeah, dz, you can see that, right? Just it's a two-dimensional domain. Okay, in the I put it over there, and yeah, this is this is a x y. Okay, z. Yeah, that's a dz. Okay. Okay, that's a one way to do. Another way is another way you can do is you begin, the same potato, right? Same, that's okay. So it's in the xy plane. I projected to the domain here, D. Okay, so D is fixed. Okay, so this will be the double integral. Okay, now here for each xy in, I don't know, so many phone calls today. For each xy in D, okay, and you draw the line going through, here's xy. You draw the line going through the potato, right? Okay, you want to figure out what is upper bound for the z, what is lower bound for the z. So z has upper bound, lower bound. Okay, upper bound, let's call it let's use h2 xy, right? Lower bound is h1 xy. So then you have h1 xy and h2 xy, and here's a function xyz and dz and the dA. Okay, so there are two different ways to set up the iterative integrals. Okay, you can begin with a double integral, then and the inside is a single integral, or you can begin with a single integral, then inside is a double integral. Okay, so it depends on the problem. Sometimes the one is better than the other one. Just like we know we were double integral, right? you have two iterative integrals for a double integral, and sometimes one of them is better than another one when you evaluate. Okay. So that is what I want to talk about today. And not if the triple integral the method is not mentioned, then you have choices. You don't need to use polar coordinates. You don't use you don't need to use spherical coordinates, or don't need to use cylindrical coordinates. You can use this directly. You can set up the iterative integral and to evaluate. The last problem I did here, I showed to you, and I found out even better without using spherical coordinates. I just set up the iterative integral, okay? And I end up with a very simple integral, so I can quickly evaluate. It takes much less time, okay? So I'm going to stop here.